Can you see the blank page, white page?
Yes, sir.
Yeah. So welcome back to the power generation system lectures again. We had a break. Now I will move on to solar energy, solar photovoltaics systems and solar energy based power plants. Then a small part of economics is also involved with solar energy. So I'll record this lecture 1 minute. Okay, recording started. Okay, now before moving on to solar energy, we'll just see what all energy conversion techniques we discussed in general, and what all we will be discussing in this course. Just we'll have a recap. So we have nuclear in this course, then thermal is there, then chemical. What all are there in chemical form? We have coal, oil. See, these are fuels. Okay, fuels in the chemical form, but it will be converted to another form. So it can be gas or oil or coal or biomass or maybe hydrogen also. So this chemical energy is converted to thermal energy. Then sometimes the thermal energy itself through heat engines. So this is the fuel. Okay, this is the fuel. This is the fuel part. Through thermal systems, it is converted through heat engines to mechanical energy. Okay, mechanical energy. Then from mechanical through electric generators, it is converted to electrical energy. So again here it is converted to electrical energy. Now sometimes this in hydro, what happens is the gravitational force on the falling water is converted to mechanical energy. Okay, converted to mechanical energy. Now here wind speed can be used to hit the blades of the wind turbine to convert it to mechanical energy. Okay, sometimes solar is used here. Solar is used through photovoltaic conversion. It is directly converted to electrical energy. Okay, now let's see the generic efficiencies of these systems. So here you see the chemical energy stored in the fossil fuels is being converted to is converted to usable forms of energy via heat by burning, and this can have an efficiency of maybe 90%. 90% here. This heating part. Okay, the chemical to heat part. Then through heat engines it is converted to mechanical energy. So again here another step is there. Here normally the efficiency can be less than or equal to 60%. Okay, so these two steps should be considered while finding the full efficiency of the system. All these efficiencies should be considered. Now again, from mechanical to electrical energy, if there is a conversion, then this electrical generator should have an efficiency, right? So normally the electrical generator efficiency can be around 90%, but I'm writing here 90%. Okay. Now, in some cases, solar is converted to thermal directly. This is what is solar thermal technology that we'll discuss later, but this is just an overall idea. Then electrical energy can be used to, here through electrolyzers, it can be used to convert to chemical energy. Then chemical to electrical through fuel cells. Here, this is fuel cells. So these are the basic things. Different energy carriers and how we utilize them. Now, when we come to solar energy in particular, so we are now going to discuss about solar energy only. So when we come to solar energy, what is the basic working principle of solar energy? Anybody?
Photoelectric emissions.
Yeah, photoelectric emissions in the sense light is absorbed by some material. I'm just saying, I'm just terming it as material now. So light is absorbed by some material. Then afterwards, what will happen? Because of the absorption of light, what will happen? Some potential difference is created because of a working principle. What is the working principle there? What we need is a potential difference so that the circuit can be completed by connecting a load, and the load can be fed with a current or a voltage supplied, and through the voltage supplied, if it's a closed circuit, we can drive a current through the circuit. So for that, this potential difference should be created first. So what is the technology behind that? See, are you going through the course electron devices now?
Yes, sir.
Yes.
Yes.
So you might be knowing better than me actually. So what is a PN junction effect for producing a potential difference? How is it produced?
Sir, he started that last class and he's not classes for the next 2 weeks.
Okay, so let me just have a small introduction to the working principle of solar photovoltaic. We will just go through a very simple model. Okay, so the working principle of solar cells is based on photovoltaic effect. So the generation of a potential difference at the junction of two different materials. We can call it as P material or N material or whatever. We'll go to that later. In response to the electromagnetic radiation. So the potential difference is created at the junction of two different materials in response to electromagnetic radiation. So the photovoltaic effect is related to photoelectric effect, where electrons are emitted from a material which absorbs light at a particular frequency. In 1905, Albert Einstein explained this by assuming that the light consists of well-defined energy quanta called photons, basically packets of energy. So that is what is quanta called photons. Then energy of such a photon is given by E equals h into f. What is h here? H is the Planck's constant and f is the frequency of the light, which is absorbed by the material. Okay, the material is designed so that it will create a potential difference. That is what is the design part consists of. Design part of the solar panel consists of. Now, the photovoltaic effect can be divided into three basic processes. In the first process, we define it as generation of charge carriers, generation of charge carriers due to the absorption of photons. This photons are absorbed by the material that form the PN junction. Okay, the material that forms a junction. Okay, so absorption of a photon in a material means that its energy is used to excite an electron from an initial energy level. Initial energy level, I am representing it as EI. So the electrons are excited from this energy level to another energy level, which is EF. Okay, so photons can only be absorbed if electron energy levels EI and EF are present, so that their difference equals the photon energy itself. What is the photon energy? Photon energy is E equals HF, right? So this gives the electron the excitation from the initial energy level EI to EF. So the difference in energy levels is EF minus EI, which is the energy provided by the photon E. So this is HF, right? So HF equals EF minus EI. Okay. Now, in an ideal semiconductor, these electrons are populated at energy levels below the so-called valence band edge. So we have two bands. Valence band edge is represented by EV. The energy in the valence band edge is represented by EV, and energy in the conduction band edge is represented by EC. So I'll draw the figure in detail here. So this is the this is one. Here I represent it as EC, then here I represent it as EV. Okay, so here this difference, here we have the energy in the gap. So this is EG. Okay, so from here if the electron jumps to another energy level, then it attains an energy EF from an initial energy level EI. This EF minus EI equals HF. Okay. Now, when this electron is jumped to another state, here there is a void. How will we represent this void? What will we call for this void?
Holes.
Hole. Yeah, so hole. So basically what we have now is electron hole pair. Okay, so generation of electron hole pair. This happened because of the absorption of the energy from the photons, which is HF. Okay, E equals HF, which created the difference between EI and EF. Okay, so this is the very basic principle of photovoltaic energy conversion. Now, so the band gap energy, the energy difference in the band gap energy is known as the EG, which is equal to EC minus EV, which is the energy levels, the difference in energy levels between the conduction band and the valence band. So if a photon with an energy smaller than EG in the sense this one, this is EG. Okay, smaller than EG reaches an ideal semiconductor. It will not be absorbed, but will traverse through the material without any interaction. Okay, so energy of the falling light ray or photon is very important for the production of potential difference and production of the energy through the circuit to drive the load current. Okay. Now, if an electron is excited from EI to EF as shown, the void is created here at EI, right? This is what is known as a hole. So this void behaves like a particle with a positive elementary charge. That is how we represent it, a positive elementary charge. And the absorption of a photon therefore leads to a creation of electron hole pair. Now the relative energy of the photon is converted to chemical energy of the electron hole pair. So here it is relative energy of the photon is converted to chemical energy of the electron hole pair. Okay, electron hole pair. Now, what is the maximum conversion efficiency from the radiative energy to the chemical energy? It is limited by some thermodynamic effect, because if the temperature is high, then the conversion efficiency will be low. Okay, so accordingly the efficiency will vary. So what is the efficiency of a solar panel from the first stage, the input stage, to the final output stage? What is the efficiency of a solar panel? Anybody?
30%.
30 is too much actually. It will not be 30%. So you can just go through some literature to find the range of efficiencies. Okay, in the next lecture I will we'll have a discussion on the range of efficiencies. Why we are using the solar panel still I mean, even if we have a very low efficiency, that also we'll discuss. So go through some, you just Google, you will get some results. Based on that, we'll have a discussion. Now, in the second process, so what was the first process? First step was the generation of charge carriers, which is the electron hole pairs, due to the absorption of photons in the materials that form a junction. Okay. Now the second one is subsequent separation of the photo generated charge carriers. Why we need a separation? Because we need a potential difference. For that, the positive and negative charges should be populated in different locations to form a potential difference. For that, subsequent separation is needed. So that is what subsequent separation of photo generated charge carriers. Generation of charge carriers is already discussed in the first step. Now separation of the photo generated charge carriers in the junction. So usually the electron hole pairs will recombine. Then the electron will fall back to the initial energy level EI. Okay, so the energy will then be released either as photon or transferred to other electrons or holes subsequently. Okay, so if so I'll now draw a figure in which how this subsequent separation is happening. So here I have, okay, here. So what I need is, I want the holes to be populated in one section here, the holes to be populated in one section. I want the electrons to be populated in another section, so that I'll get, if there is a membrane which allows these charges to flow, electrons and holes to flow, then we can channelize the flow of these charges through such a material. Accordingly, if we design the material, then we can channelize its movement. So here I'll get the movement of charges, so electrons, and here like this I will get a circuit, I mean movement of charges through a circuit if the circuit is closed. Now for that, what I do is absorption of a photon here, absorption of a photon leads to the generation of an electron hole pair. So electron hole pairs are here. Okay, electron hole pairs are here. Now the electrons and holes will recombine. Then what will happen? With some semi-permeable membrane, the electrons and holes can be separated. So here we have a membrane, here we have a membrane. So using this can be separated. Okay, now the separated electrons can be used to, these separated electrons. So here I see holes. For holes I am not shading this. Okay, for electrons I am shading this. So here I have electrons. So I have holes here, I have electrons here. The separated electrons can be used to drive an electric circuit. So after the electrons pass through the circuit, they will recombine with holes. After it flows like this, they will recombine with the holes. Okay, so this is what happens. So the semi-permeable membrane, which allows the motion of the charges, that should be designed using particular material. That is what is done with the design of solar panels in general. So now the semi-permeable membranes must be present on both sides of the absorber. So this is the absorber. Okay, this is the absorber part. Semi-permeable membranes are here. Okay, semi-permeable membranes are here. So the electrons only can flow out through one membrane. So electrons will flow through this membrane. Okay, then the holes can only flow out through the other membrane, this membrane. Okay, now these membranes are formed by N and P type materials. That is what forms a PN junction in general in semiconductor based devices. So a solar cell has to be designed such that the electrons and holes can reach the membranes before they recombine. The time it requires. So once here electrons or holes are formed, If we wait for some time, it will recombine. Before that, we'll segregate it through these two membranes, and we allow the charges to flow through the circuit and recombine, so that we will get the potential difference for the load across the load. So that is what is done. So the time it requires the charge carriers to reach the membranes must be shorter than their lifetime, the lifetime of the charge itself. It should be done in a very fast manner. Okay. So this is the second step. In the second step, what we do is the subsequent separation of the photo-generated charge carriers in the junction. In the first step, it was a generation of charge carriers due to the absorption of photons in the materials that form a junction. Now, in the third step, what is the third step? In the third step, collection of photo-generated charge carriers at the terminals of the junction. So finally, the charge carriers are extracted from the solar cells with electrical contacts. So it can perform work in an external circuit. In an external circuit, in the sense, suppose this is the panel. So such a potential difference we get, right? So this potential difference is created because of the photovoltaic effect, the PV effect, and the load is, this is the load. Okay, so this is driven because of this potential difference, we drive a current through the external circuit. So this is what is the external circuit. It can be a load or it can be another circuit, a big circuit. Okay, that is what. So the chemical energy of the electron hole pairs, is finally converted to electrical energy. So now how many stages are there? Initially, what was done? The relative energy of the photon was converted to chemical energy of the electron hole pair, right? Electron hole pair, and the chemical energy of the electron hole pair is converted to electrical energy, which is supplied to the load. Now, so this is the basic principle of solar photovoltaic conversion. So what we are going to do is, 1 minute, let me